Good afternoon. My name is Dewan, and I'm an independent consultant with Asset Optimization Services. I have about 30 years of experience in the paper industry, having worked at good companies like Beloit Corporation and Champion International. Today we are going to talk about system design to handle recycled fibers. Now, we have already discussed, you probably have discussed all the other unit operations in a way that you understand the unit operations. The whole question is, how do you design all the unit operations to work in harmony, and why do you want to do that? So basically we are talking of a system design, how to put together a system to handle recycled fibers. So the first simple thing in a recycled fiber is why we are going to do it. It's the goal. Goal is to maximize profitability of the paper mill operations. If there is no profits, nobody needs you. So then the paper mill operations profitability is the key thing. Next, what is the function? Function of a recycled fiber system is to deliver a uniform quality of a blend of recycled fibers, fines, chemicals, water, heat to the paper machine. That's the key thing. Your customer is the paper machine. If there is no customer, there is no need for the recycled fiber system. So the customer in most whether you're making pulp or just in a integrated mill, your customer is the paper machine. Hence, you must provide uniform, and this is the key word, uniform quality of fiber, fines, chemicals, water and heat to the machine. Everybody hears a lot of complaints from the paper machine, or that's your customer. There are all kinds of contaminations, there are all kinds of problems that happen on the paper machine, and hence what are these problems? One of them, if you heard so far in unit operations, some of the contamination that you've been trying to take out are sticky problems. Freeness, understand the drainage of the fiber, it varies, lowers the bulk. This is recycled fiber. Tendency to lint, or recycled fibers have a bigger tendency to lint. It degrades, lower the burst and tensile, lower stiffness, higher dirt count. Obviously, that's the biggest problem or complaint that comes from paper machines. Dirt can be dirt itself or what we call ink also. Variable brightness, now that affects the quality directly. Color variations and microbiological controls. So basically, to avoid or minimize most of these problems, you need to design your recycled fiber system must balance. Basically, what is a system balance? System balance is basically preservation of mass. What goes in must come out, and so if A is your total of recycled fiber and contaminants, and you take all your contaminants out, along with that you will also throw some fiber. That's a fundamental rule. So out throws is a total of recycled fiber, some recycled fibers and contaminations, and ultimate recycled pulp is B. So A is equal to B plus C, which is the total mass preservation. That's a fundamental, and we have to preserve that. There's nothing we can do about it. The system design concept that we are going to follow is definition of process. The other system geometry, we'll talk about unit operation efficiency, effective rejects handling, how does the system run and whether it's reliable or not, and what are the common economics, and compromises. That's the important topic or item to understand, because no matter what you do, there will be compromises in the end. So the first one, definition of a process. We are going to talk about incoming furnish. What is furnish? Furnish is incoming is the furnish is the total raw material, fiber, chemicals, water, heat, all coming in. Outgoing end product to the paper machine, process efficiency, and how do you evaluate that efficiency. So first, let's start with the incoming furnish. It's incoming furnish right now here we are referring to is first the raw material. Price and quality are the most important for successful operation. Price, the cheaper you can buy, the better it is, and quality, the highest quality that you can get, the better off you are. The common grades of recycled fiber, there are many grades, but they have been classified into many grades, but the common ones are corrugated, which is OCC, mixed waste, or MOW, news, ONP, office waste, can be SOW, and direct entry also, which has very little contamination. recycled fiber is a secondary material. So, no matter what happens, because it is collected manually, it will never be technically perfect. It will never be as technically perfect as pulp, like a chemical pulp from the pulp mill. Incoming contamination, that contaminants that come with the recycled fiber are many, and they have been classified. Some of them have been classified as prohibitive materials, which is any material that is in excess, that in excess will make the furnish unsuitable. It could be metals, plastics, it could be carbon paper in OCC, or white leather, inks, resins. These are all prohibitive materials. And then throwouts. Throwout are just most generally are the fibrous throwouts, or any paper that will make the furnish unsuitable for specified grade. In other words, if carbon paper is mixed in white ledger or mixed papers or news in OCC, it's not acceptable. So those have to be taken out. Those are throwouts. So a combination of prohibitive materials and throwouts and other some of the fiber, good fiber that is lost in a recycled plant, total of those are called outthrows. Then in a system, once we define what the incoming furnish and contamination is, we also need to define what is the end product or the outgoing end product. So since recycled fibers are used in most paper grades manufactured today, this end quality and end product is very important. Recycled fiber produced in a plant must meet customer quality specifications. Once again, the customer is the paper machine. So the quality here is directly proportional to the contaminant rejection efficiency of the system and inversely proportional to the contaminant level in the furnish. What does that mean? So in a system, if C is the number of contaminants coming in and you got E as a rejection efficiency of the entire system, and Q is the end product quality that you must have. And how do you define quality? Can be many different ways, but right now we are not trying to define quality, but basically we are saying Q is equal to E over C. In other words, if your efficiency improves, your quality will improve. Your outthrows may increase, but your quality will improve. Or if your number of contamination decreases and your efficiency stays the same, your quality will improve, however you define quality. And then efficiency evaluation. How do you evaluate the efficiency? That can be in many different ways in different mills. So, but you must define what determine the type of contamination that you have, establish the efficiency of each module. Again, I will come back to what is a module, and measure all the inputs and outputs. Once you do that, then you can define the efficiency of each module or the entire system. And basically it can be different ways that generally every mill defines the overall efficiency of the mill or each module in different ways. But no matter how you define it, once you define it, you have to be consistent. If you are trying to compare one module with another module or one plant with another plant, you have to be consistent in how you define or how do you evaluate the efficiency or the methodology. And continuing with types of contamination. Okay, what is the most important thing in a system is what are the type of contaminants you are getting and what are you trying to get rid of. So a lot of people have defined contamination or classified different contaminants in different way. Here is just a simplistic way of defining the contaminants in terms of high density and low density contaminants. High density, heavy and rigid, as you can see, heavy and rigid contamination, and then there can be metals, staples, screws, paper clips, etc., and then debris, sand, grit, glass also. High density but light and soft could be metal foils, rust, reinforcing mesh, paper cores, boards, synthetic fibers. They are a little heavy. Carpets, cork. And then low density. Low density can be basically defined as density lower than the water, and they can be defined again, classified into non-deformable and deformable. And some of the non-deformables are the brittle plastics or sealing tapes, rubber, and that's the hard rubber. And then deformables are the hot melts, adhesives, waxes, natural resins, grease, styrofoam, polyethylene, etc. And finally the carbon papers and toweling. Toweling, because it contains a lot of wet strength, it generally gets rejected. All right, system design concepts. Basically we define the system design divided into 3 sections: process configurations, modules, operating parameters, and module compatibility. So what's a module? So basic modules, a module is basically a combination of stages of a screening system or a pulping area or a cleaning system or washing or whatever. So these are the modules that you've already studied under various different lessons plans. So basic modules required to process recycled fiber will depend on available furnish, type and quality, and desired end product and quality. Again, it comes back to the same thing: what is coming in and what do you want out. So each module performs a specific function that must be well defined. What are these modules? Here are the modules: basic pulping, high density cleaning, coarse screening, fine screening, flotation cleaning, then again screening, very ultrafine, washing, thickening, dispersion, bleaching, rejects handling, and water clarification. These are the basic modules that you have already studied and gone through. So basically each module has a specific function in that must be well defined. What are you trying to remove? What are you trying to achieve in each module? And that's how you put together these modules, and you can put them in any sequence you want, but again you have to define what you're trying to do and how you're trying to do it. This is just an example of a system or connecting different modules. No existing system is like that, but I just put in this together for you to look at it and be able to critique it and be able to understand that different modules can be connected in different ways depending on what is the incoming material and its quality and what is the end product and the desired quality. So here you can see I have started out with the high density pulpers, some chests, and going to coarse screening and cleaning, then fine screening, flotation, cleaning, and washing. And washing, remember, always has to be accumulated with water clarification so that you can recycle some of the water back. Then thickening, dispersion, first stage of bleaching. Again, I used hypo bleaching, which is not predominantly generally used these days, but it's just to tweak your interest in it. And washer, and then peroxide bleaching, and again a washer, and then finally to the chest and to the paper machine. Again I show peroxide, and if you can imagine what kind of a system it would be generally be using mixed office waste or solid office waste for de-inking. And obviously this mill is producing some colored papers so that you can bring some colored broke and put it back into the system, and maybe that's why we can use hypo, or we can use something else. And that is basically going back to your bleaching lesson. Operating parameters. What are the operating parameters that we must function under? Basically I have defined all the modules under different operating condition the operating parameters, and I've divided them up into stock conditions and operating conditions. Stock conditions are what? Means what are the contamination or type of contaminants you have, what is the consistency of the system, of the flow stream that are going in the system in each module, temperature in each module, freeness, pH, and air content in each module. Then operating conditions. If you have screens, what are the holes or the slot sizes, or whether it's in washing, what's the mesh size, reject rates in each stage, pressure differential, what is the pressure difference between feed and accepts, specific energy, how much energy is being used, probability of removal. Let's talk about that a little bit. We've already probably talked about that in your screens and cleaners. Probability of removal is what is the efficiency? So how are you going to remove them, and what will be the probability? Now in a screens there may be a higher probability of removing rigid stuff, but in a cleaner the higher probability is based on specific density, and hence so the probability in the two cases would be different for different contamination. Then of course the residence time. Okay, module compatibility. As the name says, module compatibility, operation of any module affects the operation of the subsequent module and its efficiency. What does that mean? Now if you have a pulping module and a screening module following it, depending on what contamination you remove in the pulping, it will affect the efficiency of the screening module, which comes after that. So subsequent efficiency of a subsequent module is definitely affected by the one before. Then next, compatibility in operating parameters. We will come to the operating parameters again. And efficiency must exist between each module to optimize system efficiency. That basically, if you have a 3-stage screening system, you must have compatibility within the system itself, within the module, between each unit operation. And then overall, total system thinking develops the most complete and economical solution. Why? You cannot just think of one contamination or one system to be, one module to be used like a screening or cleaning, or if you think you can do everything by a cleaning module or you can do everything by a screening module, not possible. So you really have to think in totality or have a holistic view so that you can develop the best economical solution for yourself. Modular effort. Now in each module, you understand the module, you are trying to remove contamination. So the intensity of contaminant removal in each operation in a module is this modular effort. We'll talk a little bit more about that, but right now you have to understand, if you have a screening module and you have 3 stages in it, how much effort are you going to put into removing contamination? Are you going to have very fine slots? Are you going to have some fine holes? What are you trying to remove? How much energy are you using? It is all combination of the modular effort. Excessive effort overlaps between modules leads wasted capital and operating costs. So basically, if you put very small holes in a pulping module, for example, and very small slots in a screening module following each other, you may be wasting some of the effort because you are trying to remove everything in both the modules. Or in other words, inadequate modular intensity results in gaps in removing some of the contamination. So if you have pulper with very small holes but screens with very large hole, you may not get the results that you want. Let's look at this in a little more detailed fashion. Look at this system, has pulper, screens and cleaning. Okay, here's the consistency of all the 3 operations, and here this hole size 5 millimeters in the pulper and very small slots in the screen. And you can see the efficiency allocated to them gives you an overall efficiency of 98% in the system. But basically, what are we doing here? We have taken the pulper effort from 0 to up to this point to get a 50% efficiency so that we can remove a large amount of contamination. Then what we do, we put very small slots in screen trying to remove some of the contamination that the pulper would have already removed, but we are trying to remove that and then taking it over way beyond, so that some of the screen will remove some of the contamination that we are ultimately going to remove by the cleaners. And are you going to be successful in doing that or not? So basically, in terms of effort, in terms of, you can call it in terms of how much horsepower you've used, you use extra horsepower in both the pulper and the screen by this much, and the same thing with the cleaner and the screen. And efficiency gap, you basically, if this is the efficiency you need, you basically gone to get this efficiency in a pulper, which is more than you need to have, and same thing between screen and cleaner. So but ultimately we get 98% efficiency, which is very, very good. So in this system, we've got the high contaminant removal efficiency, high cost and high energy use. Let's look the other way. Now we basically we say we're not going to do all that what we did before, so we're going to have less efficiency in the pulper by increasing the hole size, so that we pass some of that contaminant removal to the screen. But in the meantime, the screen guy has gone and put in 3 millimeter slots in the pulper in the screen, so that his overall efficiency of the screening module is gone down and the cleaning is the same. But in this case, we have a big gap between the screen and the cleaner. We have done very well between pulper and the screen now, but we have left a gap between the screen and the cleaner. So we have, in this case, an overall efficiency of only 86%. And of course, we have less contaminant removal efficiency, less cost, and also moderate energy use. So this system has some gaps in it in terms of what contaminants can be removed. Next one, we try to make it more ideal. We put in a 2 millimeter screen basket in the screen, and we cover that gap between the screen and the cleaners. So we have very little wasted effort in between the screen and the pulper or screen and the cleaners, and we are not overlapping the inefficiency of the two. So everything is working very good now, and here we get a 96% overall efficiency. Is that efficiency acceptable, that only goes by mill to mill. In this case, we have optimal contaminant removal efficiency, optimal cost and ideal energy use. However, we do not have as much efficiency or contaminant removal as we did in the first system. So, it will depend from mill to mill as to what is acceptable. Now, what is acceptable means we have two contaminants before and 4, what is the size, what is acceptable, what kind of papers you are making. So, it will be depend on all that. However, this system is ideal for whatever mill can be using this now. So, we have not wasted the modular effort or had exceedingly high overlaps in the efficiency. So, module design comes back to the design of the whole system again, and basically in here we are saying mechanical, again back to the modules, mechanical separation of contaminants based on size and rigidity is done in screening modules. And then going further, centrifugal separation of contaminants is done in the cleaning, and this is based on specific weight difference. Unit operation of all stages in modules should be compatible in contaminant removing efficiency. We just saw that. We just saw that between pulpers, screens and cleaners. So, the same thing follows with washing, thickening, flotation and the modules. And no one module can effectively remove contaminants rejected by another module, since each module is designed to remove a specific contamination. So, if screens are there with you have let us say medium slots of screens and you are working with 2 to 3 millimeter slots, and then you follow them by cleaners, that is fine. Now, what is removed in the screens is okay, but what is removed in the cleaners, if you take it back in the system, you are going to have problems. Look at this example. Here we got 3 types of contaminants coming into the screening module. We have a screening, reverse cleaning and flotation modules. We have screenable contamination coming in here, which is greater than 0.15 millimeter, and then we have some ink, and we have also lightweight contamination. So, in this system, the first top system, the screen removes all the screenable contamination, that is fine, and good fiber comes back. In the reverse cleaners, we remove all the lightweight cleaners, and that is fine. And in the ink, in the flotation, we remove all the ink, that is perfectly fine. Now, obviously, this is an exaggerated example, but so we get only good clean fiber afterwards. However, if you take the same system again and you decide to save on money and decide to have a second stage of the screens act as if it can remove all the contamination that was removed by the reverse cleaners, and we mix them up here. I mean, for example, we can have 0.2 millimeter slots here, and we can go to 0.1 millimeter slots here and say, yeah, we can remove everything but the cleaner rejects, but that is not possible. Cleaners are removing lightweights, and if these lightweights had to be removed, the screen would have removed them. So, here the second stage does not remove all of them. Some of them get removed because of the water separation or the water streams, and the rest goes back, and ultimately it does not get removed, and in the final stream we do not have just pure pulp, we have some lightweight contamination. So, the mill saved on some of the cost in trying to save on secondary stage of the reverse cleaners, but ultimately they land up in problems because they have contamination, lightweight contamination in the final stream. So, ultimately all cleanable rejects are not necessarily screenable, and again other way, all screenable rejects are not necessarily cleanable. That is a fundamental thing, and you have to remember that. If anybody says, oh, what you can do in cleaners or you do not need cleaners, I can do it in screens, can never be true. So, module design. In any given module, more than one contaminant removing stage is often necessary to reclaim fiber from the reject stream. You have seen that, the people who talked about cleaners and screens and flotation already told you about that, and basically you need more than one stage, and the second stage is basically to recover some fiber. And always the next stage is always more efficient because it receives contaminants that are conducive to rejection from the preceding stage. Now, these contaminants have already been rejected once, and if the second stage, like for example in a screen, the slot size are the same or smaller, you are going to get rejected. And each module should have its own reject stream, which should not travel to other separation modules, and I just showed you an example of that previous example. So, here are some examples of stages in the module. First, one pulping generally is single stage. Here is a screening module, co-current, where the accepts of the screen are going forward, 2-stage system, 3-stage system, cascade type or counter current, because the accepts are going backward to its preceding stage. Here's a two-stage reverse cleaning system, counterflow or cascade. And here's a four-stage modified mishmash of a system where the screen is going forward and whatever rejected is treated by reverse cleaners and forward cleaners, again here to preserve fiber balance. Again, this system is this one here is a bad example of both mixture of co-current and counter-current screens, but I have seen this in mills. It is being used. Is it a bad one? Yes. Can it be functional? Yes. So all the answers are possible. However, if you can avoid it, it's better off. So module design. So in an effort to minimize fiber loss that we already talked about, you increase the number of stages. So as the number of contaminant removal stages increases, the overall efficiency of a module of contaminant removal decreases. In other words, if you go from one stage to two stages, your contaminant removal efficiency is going to be less. If you go to three stages even further, your contaminant removal efficiency overall for this module is going to be even less. And early decontamination in a system results in better overall efficiency. That basically means remove your contamination as soon as possible and as early as possible in a system and as large as possible without breaking them down. And hence this will reduce the contaminant runaround and breakdown. Now I will show you the examples of this thing. So here's a system, screening, basically one stage, two stage, three stage, all counter current. Now the efficiency in each stage, first stage is 80%, second stage is 90, and third stage is 90. We can assuming that we have decreased the size of the slots in these stages. Then the overall contaminant removal efficiency of each module, this first module will be 80% because this is the first one. The two stages efficiency of the module will be 78%. And in this, the three-stage module will be 77%. However, you could improve this if you went to even smaller stage and could get this efficiency up to 95%, then you will approach 78%. However, basically as you can see, no matter what you do, the overall module efficiency will never be more than the efficiency of the primary stage. So 80% is the primary stage. That can be the maximum efficiency in this one stage, two stage, three stage, or even four stage. So no matter what you do, fundamentally it cannot get more than any module will not get any higher efficiency than the efficiency of the primary stage. And then effect of early decontamination. Here's a system in which a pulper, screening, and cleaning is used. The numbers are again obviously used to highlight the effect of what I'm saying, but the results are true. So in a pulper efficiency of 95, we are trying to remove as much as we possibly can. Maybe it's a drum pulper. And then we have screening and cleaning in which we have 70 and 70% efficiency. Overall efficiency of 99.5%. So if you look at these curves here, this is the first system A. We remove quite a bit of all the contamination first. And then we go to screens and then to the cleaners, and we have very little contamination left. You do the same system in which basically you say 80% efficiency in the pulper. Somebody decided to put larger holes or whatever, and then you find because of the more contamination is going to screening and cleaning, you can generally say we have higher efficiency in the screens and the cleaners. As you can see, we've got 80 and 80 here. However, the overall efficiency of the system is less than the system A, which is basically showing you that early decontamination is more effective than later decontamination. So, and this is shows the second curve. The other thing to note here is 0.4 versus 0.8 contamination. In terms of system inefficiency, this system has twice as many contaminants as this system. And what is the effect of that? Again, like I told you last time, in the last example, this is all depend on mill dependent whether what is acceptable and what is not acceptable. Okay, efficiency, unit operation efficiency, we have to talk about those. Methods of defibering are all pulping, mechanical separation done by screening, centrifugal separation by cleaning, hydraulic, flotation washing, and then we got the other modules to talk about. So first one, let's talk about the pulping module. Again, here basically the two blocks are shown here are separated into stock conditions and operating conditions. So in pulping module, high temperature improves defibering and reduces contaminant including sticky size. High consistency accelerates defibering and ink detachments. And these are all known facts that you've already studied with the other with all the unit operations. High consistency promotes ink size reduction, and high consistency reduces contaminant, including stickies, breakdown. So if you look at this both thing, high consistency does not reduce other contamination except the ink size. So in a way, it's more effective. And high pH enhances defibering because it swells the fiber up faster than in an acidic condition. Under operating conditions, proper specific energy input ensures stock circulation at a given consistency. So in pulping, consistency is dependent on how much pulp is there, but pulping time does not affect on consistency or on the energy. It basically, energy is required for circulation. As the consistency increases, more and more circulation is needed, so and more energy is needed. Smaller hole size and higher reject rates improves probability of removing large contaminants. That's fact. Longer residence time improves stock uniformity. Next, screening module. Again, you've already looked at these things. Again, stock conditions, operating conditions. High temperature and or pH reduce contaminant removal of plastics, stickies, adhesives, hot melts, because these kind of contamination becomes pliable and tend to go through the screens. Correspondingly, high pressure differential reduces contaminant removal and increases throughput. So basically, why? High pressure differential increases the throughput. That's the given fact, because screen throughput is dependent on the pressure drop, and if you're trying to increase the throughput, you're also trying to increase the passing velocity, and hence some of these kind of contaminations will go through. So this reduces the contaminant removal. Rigid contaminant removal depends on hole and slot size, and this will not depend on the probability of removal, because depending on the hole or slot size, anything bigger than them will get 100% removal. Smaller hole or slot size improves contaminant removal and reduces throughput. So high consistency or temperature or freeness increases reject rates and fractionation. You must have done this also, and reject rates are increased because the high consistency helps increase the reject rate. As the reject rate increases, contamination increases. Contamination removal increases, and high reject rate increases contaminant removal. Cleaning module, same principles apply that you've just seen in the screening module. High consistency reduces contaminant removal. High temperature increases contaminant removal. Now this is opposite to in the screens. In the screens, high temperature reduces contaminant removal, especially for the pliable and the malleable contamination, as you saw, but high temperature increases contaminant removal efficiency in a cleaner, because this is dependent on more specific gravity and viscosity, and as high temperature increases, the temperature increases, viscosity decreases. High temperature of freeness increases reject consistency in forward cleaners. That's because of freeness, and you get some fractionation. And high temperature of freeness reduces reject consistency in reverse cleaners, which is opposite to that. Again, high pressure differential increases contaminant removal efficiency and throughput. Because of the high pressure differential, you get more G velocities. High reject rate improves contaminant removal, which is a fact, and smaller cleaner sizes in diameter improves contaminant removal, because it basically improves the G forces within the cleaner itself, and hence improves the contaminant removal. But as the cleaner size decreases, it reduces the the throughput. Flotation module, again, high consistency reduces ink removal, because there is a problem between air contact between air and ink particles, but it does increase throughput. On the same side, high reject rates increase ink removal efficiency but reduces throughput. So at high consistency, if you increase reject rates, you can get higher efficiency, but your yield goes down and you lose a lot of fiber. Proper pH is a must to improve ink removal. High temperature improves ink removal. Ash content improves ink removal in flotation, and also limited removal of ash and lightweight contamination. If somebody says that you can take out a lot of ash and a lot of lightweight contamination like stickies in flotation, that's not true. It's only limited, because there's always chemistry involved in that. And same on the other side, on the operating conditions, proper air content and air bubble size distribution improves ink removal probability. Just large bubbles will not improve ink removal. Lower, just small, very micro bubbles will not improve ink removal because they just need one small bubble is not good enough to take an ink up to float, up to the surface. So the proper bubble size distribution is important in flotation. Ink size in the range of 10 to 120 microns improves removal efficiency. That's a good range for ink removal. And proper residence time is necessary for proper contact between air and the ink particles. Washing modules, high consistency improves throughput, of course, because you can get more going in it. High consistency reduces ink and or ash removal efficiency because in washing the fiber mat is formed, and as the mat is formed it traps inks and ash. High temperature and freeness improves water drainage capability, that's a given fact. High pH also reduces water drainage and washing efficiency. So we try to reduce the pH here. Large ink particles greater than 15 microns reduce washing efficiency because they get trapped between the fiber mat as it is being formed on the washer. Smaller aperture or wire mesh size reduces fiber loss, improves throughput, but it also reduces how much ink you are trying to wash away. Larger mesh size improves ink or ash washing efficiency but increases fiber loss. Washing through fiber mat reduces efficiency. Now, depending on the type of washer you have, and if it's forming a very good mat or a tight mat, it will reduce washing efficiency. Like things like disc filters or vacuum filters will reduce washing efficiency. Things like deckers or high speed or dynamic washers will improve washing. Turbulent washing, which is the dynamic washers, improves ink ash removal but increases fiber loss. Thickening model, we are basically removing water here, and basic same principles apply, that high consistency will improve throughput, large mesh size will improve thickening efficiency but increases fiber loss. Dispersion module, now this is another one important one where you have to understand these are the operating conditions. High consistency and high temperature improves contaminant size reduction capability. High consistency because it enhances fiber to fiber rubbing or shear actions, so improves contaminant reduction, size reduction efficiency. And here we are talking about in contaminants that is like inks and dispersion of hot melt, stickies and asphalt and waxes. However, contaminants like styrofoam, polyplastic, latex do not disperse. They are much more rigid or much more cohesive and will not shear off in high shear kneading or dispersion. And here low specific energy in the operating conditions used for ink fiber detachment. This is in the kneaders where we are just rubbing, and it's like a dough mixing where we are just rubbing fiber to fiber. Low energy is necessary for, is enough for ink to fiber detachment. That's all we are trying to do. In high specific dispersion modules where we are trying to disperse the contamination and reduce the size to lower than 50 microns. Lower than 50 microns, why? Because that's where the human eye makes a distinguish between what you can see and what you cannot see. So once you, the whole point of doing dispersion is so that any ink that is left in there or any other contamination, the human eye should not be able to see it. And high specific energy can reduce freeness and modify fiber characteristics. It can either improve the strength or decrease the strength. If the residence time is very high in dispersion, then it can reduce, or you put a lot of energy in there and you get some cutting, it reduces the fiber strength and reduces the freeness. If you just do enough at a very high consistency, then you are not reducing the freeness by that much, and you can actually help yourself in improving fiber strength. And of course, mixing, both dispersion and kneading is basically a mixing process where you can mix chemicals if you want to, but it also mixes the whole stock and improves stock uniformity and homogeneity and aesthetics. Bleaching modules, I've already been through those bleaching modules with the right bleaching lesson, but proper temperature, consistency, pH are important to maximize bleaching efficiency, and also depends on where the chemicals are added. Higher consistency and temperature reduce cost of bleaching, and only fibers can be bleached, and chemicals depend on fiber type, whether you are using chemical fibers or mechanical fiber. And you've probably seen that you can use, for example, sodium hydrosulfide or mechanical pulps, and you will probably can use some other chemicals for chemical types like peroxide better. And then proper residence time is critical to complete the bleach chemical reaction, and bleaching or color removal of carbon particles is not possible. Carbon particles will not be cannot be bleached, and this black color cannot be changed by no matter what means you have. The only thing you can do is you remove them and or disperse them by through size reduction so that humans' eyes cannot see. Rejects module is one of the very important module which has to be there, and we've talked about that in 2 or 3 examples properly, that we must handle the rejects carefully and properly so that they are not recycled back into the system. Solids or water rejected at a module should not be recycled back to any other module in the system. Recycling rejects will increase the amount of contamination and reduce end product quality. We've seen that example before. High temperature, high consistency and low pH improve rejects thickening. It depends on how you remove them, and we'll talk about those just a little bit more. Reject solids should be discarded from the system. Do not recycle them. If you can possibly handle them and discard them, it's better off. You got to do that. Solids could be thickened for transportation to another site so that you can decrease the cost of transportation and landfilling. Rejected water should be treated, clarified before being reused in the system. Again, I'll talk about that a little bit, but any rejects water should not be recycled back in the system because it will have contamination in it. And water clarification module, which is a very, very important, either you do it on a washing stage or you do it on a reject stage, rejects handling stage. Low consistency and high temperature improve water clarification. Low consistency depends on the kind of a water clarifier you use. Generally, most people use dissolved air flotation clarifier, which is better for removing inks, fiber, lightweight contamination like stickies and waxes, and those are the contamination we are mostly concerned with. Anything that is heavy and solid or rigid is more easily removed during the thickening part of it, and all the water that's left afterwards contains most of these contamination. Settling clarifier is better for ash removal and other heavier weight contamination. High residence time in the clarifier improves clarification. So let's look at rejects handling now. We have looked at all the operating modules. We have looked at their conditions, operating conditions, stock conditions. We know the modules. We basically summarized all the modules, all the unit operations, so that you can design them carefully. Now you've seen how many number of variables that you've had in them. As the number of variables increase, the choices will also improve or increase, and many different vendors have come up with different modules or geometry of the modules so that you can take advantage of their equipment. However, rejects handling is probably one of the most important modules, so that in the recycled fiber system you have to be able to reject all the contamination out of the system. Now, to do that, we must maintain contaminant integrity, because if you let the contamination run around or reduce in size, the system is going to be in trouble. Rejects module compatibility with the main modules, like the main unit operations or the modules, and what is the removing efficiency. Integrity. Important to maintain rejected contaminant size. If you let the contaminants be reduced in size, the chances are you will need more modules, or you will need more, or you will have a runaround and you will need more system, or you will have more system contamination, and end product will have more contamination. And we will talk a little bit more about that, but you've seen that in the other example where we took the cleaner rejects and back into the screens and we had problems. And that's why we were talking about early decontamination is very, very important, and that improves system efficiency. And you saw that because in a pulping module, as you can increase or take out as many contamination as possible as early in the system in the original sizes, the better off you are. Rejects from any module should not be recycled to another module to avoid recontamination and or contaminant size reduction. We just saw that. Previously we saw an example of that. Plus, as you've learned under the stickies lesson, that macro stickies will break down into micro stickies, and micro stickies cannot be taken out. They can be dispersed, yes, or they can be fixed with chemicals to the fiber so that they don't make problem on the paper machine, but they cannot be removed. So if you have a runaround in the system, the chances are that you will you will increase the contamination in the end product. And rejects from all modules must be prepared, thickened and or clarified for landfill or incineration using cost-effective technology, especially if filtrate needs to be reused. Filtrate means filtrate from the contaminations. So here's an example to show you what some mills have done and which is a better one and which is not good. Here you can see there is no compatibility between modules and rejects treatment. The system is very good. We got pulping, screening, forward cleaners, flotation, reverse cleaners, and we got all rejects coming out. This is all so far very good. But in many mills what they do is combine all the rejects together and put them in a rejects thickening module. They thicken the rejects and send them to the landfill. That's well and good, but all the water that's left over, they bring it back and put it in the pulper. So what's in this water? We just talked about that in this, all this water is full of all this contamination, which is fiber, lightweight contamination like stickies, waxes, etc. So once you do that, what have you done? You basically increase the load on the rest of the system in terms of lightweight contamination, stickies, and some sand, some grit, and now all of these are going to get overworked and their efficiency is not going to be as good. So overall system efficiency goes down. Sure, you have saved some money here by not treating this water. In the next system, we do the same thing, but we treat this water by a clarifier, dissolved air, flotation clarifier preferably, and take some system bleed out, throw some water away and pass and takes most of the water back in the system. Here we have done this so that we can remove all the inks and the some fillers, some stickies, some waxes, some fiber that was in this stream from the thickening module here and remove them. That improved the system much better, and hence these screens efficiency of all these modules will be kept what they were designed for. And we must take a system bleed, because once you do that, you don't want to close the system in a way that your chemical balance will be upset. So this helps maintain the chemical balance. So contaminant removal efficiency. Rejects should not travel between modules, since no one module can effectively remove from the system the rejects of another module. We already saw that previously, that we should not recycle contamination from one module, for example, or from a cleaner module to a screening module, or even from a screening module to a screening module, unless the second or the third stage in the screening where you're taking the contamination is made compatible with the subsequent module, not with the preceding but the next module. So you have to maintain compatibility between the modules, and also between compatibility in how you're going to reject or take care of all the rejects, so the rejects are not recycled and do not run around and break down. So rejects treatment efficiency should be equivalent to the system efficiency to prevent recontamination of the system. So this is important. If you want to remove all the contamination, but you remove only 50% of the contaminants in the rejects module, then the rest are going to get recycled and run around and cause problems. Reject system must successfully integrate with the entire mill wastewater treatment system. Now in the last, this we showed here, if you are throwing away some of the water bleed into the mill waste treatment or water treatment system, this must be compatible. If it's not, the mill wastewater treatment system will say, we don't want your water from the de-ink system or from the recycled fiber system, and they are in trouble then. Okay, next. So hopefully everything so far is clear, that every module must be designed carefully so that they are compatible to each other. And the rejects should be handled such that you keep the efficiency, contaminant removal efficiency of each module the way you intended it to be designed. You cannot compromise on those things. However, all these things must be put together in a sequence so that you have what you call hydraulic synergism between modules and unit operations, and this is runnability. As you maintain hydraulics synergy between each module and each unit operation, you're better off. In other words, you're passing from one module to another module, and the consistencies and the flows and the temperatures are all in sync with each other. Reliability, what does that mean? Basically product uniformity, again the word uniformity comes in the picture here, or the ability to provide the right product at all times in the proper quantity and quality. This is to your customer, which is the paper machine people. They want the proper quantity and the quality at all times. Whether they go up in production or go down in production, you need to be providing uniform product and quality and quantity. And that's why this system, that a recycled fiber system, must be able to go up or down in a way that is reliable, be able to handle all kinds of operating conditions at all times. Runnability, which is the hydraulic synergy between each module. So each module must run in hydraulic balance within itself and with other modules through proper design of pumps and interconnecting pipes. In other words, you cannot design one module to run 1000 gallons per minute and the other module is designed to run only 500 gallons per minute. So what happens to the other one? So basically you have to maintain some hydraulic synergy. You cannot design one module to run at a consistency far greater than the other module when the other module cannot handle that consistency. So you have to design a system in a way that it can handle all the consistencies, pressures, temperatures, and the flows. And the same thing with the temperature. You can't have one module at a cold temperature and suddenly expect it to be going up and treat the other one at a higher temperature. System should react fast during upset conditions. What are the upset conditions? Could be a startup, could be a shutdown. System should be able to react fast in those conditions. Sometimes paper machines shut down or stop for some reason and this whole recycled fiber system has to back up. So that's another upset condition. All modules should restabilize and reach equilibrium relatively quickly. Now what does that mean? Basically that you must reach steady state condition very, very fast. You can't have screening system all ready to go and flotation system is not ready to go because it has not reached a steady state. Now that's an upset condition and you should not have a design like that. System should be easy for operator to understand and to control under all conditions. All conditions, again, startup conditions, shutdown conditions, so equipment breakdown conditions, quality upset conditions or production upset condition. Runnability, again is the hydraulic synergism or hydraulic synergy between each modules, and the key operating factors that must be controlled to ensure system runnability are pressure, consistency, level, flow, and time in chest and equipment. Without these things under control, you will not be able to get hydraulic synergy or steady state between the modules. All the above are interrelated such that variation in any one changes the other. Controls, basically that's what we said here, the key operating factor that must be controlled, and hence what are the controlling? We're controlling pressure, temperature, consistency, flow. Variations in pressure will affect flow, which affects consistency. Variations in flow will affect consistency, of course. It will affect level in different chests, and of course will have effect on time. Excuse me. Variations in consistency affect pressure. Variations in level will affect pressure and time depending on in a chest. If the level goes up and down, the flow will change and the pressure to the pump suction, for example, will change, and that will affect the output pressure of the pump, and the flow will change, that will affect the time in the stock chest. So variations in time affect uniformity of stock and hence runnability of unit operations, which affect flow, consistency, level, and also pressure. So as you can see, all these things are very, very important to be controlled so that you can maintain hydraulic synergy between each module and each unit operation. Reliability. Now, if the system is not reliable, what the first thing the mill manager or the production manager does? He says, I can't rely on that system to give me what? Uniform product, quality, and quantity. So why should I run it? I cannot upset my paper machine, which is the prime thing, because that's what makes the money in a paper mill. So reliability, effective system controls are essential to ensure that process runnability under all conditions. And again, conditions can be all, like I told you, startup conditions, shutdown conditions, quality conditions. Regulation and adjustments of the operating parameters, process optimization. Okay, all processes must be optimized, and regulation and adjustments of the operating parameters, it should be for process optimization. Proper contaminant removal and disposal. We've already talked about that. Provide catch-up ability in case of unpredicted downtime in module inefficiency. Other module inefficiency, there's a screen basket has a hole in it, or a cleaner has blown, or washing efficiency is not working out, or the flotation is upset, so you have problems. So then you have to shut down, wash up, start all over again, reach equilibrium, and come to a steady state. If that's the case, you have a problem in catch-up. The system must have some built-in catch-up capacity so that you can make up and not put the paper machine in jeopardy so that you run out of stock, and be able to also control product quality and production rate. So the controls are very, very important system controls, and most people are now using DCS controls so that you can put in all kinds of algorithms and everything else so that you can control your process in much more improved manner now than it was possible 10 years ago even. So benefits. So finally, what are the benefits of a properly designed system? We've all seen and heard now, but that we should be able to handle variation in incoming furnish. Nobody can say that the incoming raw material is always of the same quality. It always keeps changing. You never know from day to day. So, but more important thing is that you control quality, incoming quality, or control the contamination that's coming in with the raw material. Operators should be able to easily adjust output capacity depending on the paper machine. Steady operation and reaches steady state or equilibrium quickly. Requires minimum operator attention. That's where the again system controls come into picture. If operator requires constant attention, then either the system is not going to get the attention from the operator, or your system is in a upset condition most of the time. Then also optimum use of energy and minimum fiber loss. That's how you design the system to make sure that you get those. Uniform end product quality and high paper machine efficiency. These are very important, and obviously optimum operating cost dollars per ton. You don't want to be spending a lot more than you should be, so that you have to be in a way more economical to be able to use this pulp. If this pulp, recycled pulp, is more expensive than other pulps, mill will tend to use those other pulps. Finally, economics and compromises. We said we have to understand what are the compromises that we must make in designing a system. Why? Because the ultimate operating cost and capital cost and the return on investment matter on how much can we spend, what are we getting in, what are we making out, or the end product is, and what quality and quantity do we want. So system value is the capital cost or the operating cost, and product quantity and quality, what do we want. So this is where we have to finally bear down, decide what is the return on the investment we have and what compromises do we need to make to get that investment. So every system has a technological value proportional to its capital and operating cost, and you can put that value in terms of dollars or in terms of dollars per ton, or however you want to define it. However, for a given system technology, in other words, all the modules that you put together in the sequence that you put together, that's the system technology. End product quality is proportional to the system value and system outthrows, which is the total of fiber and contamination. How? Let's look at that. Here's a system of pulping and screening. I've given you the efficiencies of each screen. This is a cascade system. In other words, accepts of the secondary screen are going back to the primary screen. System efficiency overall is 80%. However, since this is going back, as you can see from the pulping, you got 60 contaminants. Now we got 80 contaminants going back. You need a bigger screen, hence you need more energy here. Next one, here is the secondary screen accept going forward. So the feed stream to the primary screen is smaller. However, because this is going forward, we have more contamination going forward, and overall system efficiency is 70%. So what are the key differences between the two systems? A system B is 10 to 15% less than system A in terms of its cost, because we use smaller screens in B because we had less number of contamination to be handled. Second, energy used by system B is less, 15 to 20% less in system A. Why? Because we could use a smaller screen, smaller primary screen in system B right there, because we have less flow stream coming, a smaller flow stream coming into the primary screen. However, we have compromised screening efficiency of system B is 10% less than system A. Now in some mills, this compromise is acceptable. Let's say assume a mill which had no screens, and now they got some money available to put in a screening system, and all they can do is to put 70% efficiency only. To them, the system is 70% more efficient. However, if there is a system already existing which is giving 80%, and now somebody says the baskets are too expensive, let's open them up, I want more production capacity, and they design system A into system B. Now you got less